So we covered, isotopes and ions already. We also covered Lewis structure earlier last week. We talked about how elements like to hold hands to make bonds. And we're going to take that little bonding piece a little bit further. We're talking about those ions. So we're going to talk about ions today with bonding. So let's switch to our screen here. Okay. So our focus for this one is ionic bonds. All right. Remember this right here? Well, never mind. I won't say that because you kind of know it. You got ionic bonds. The key part with ionic bonds is it occurs between a metal and a non-metal, such as sodium and chlorine. Move my screen's over this monitor over here. All right, so I'm not doing this so much. Cool. So I have sodium and chlorine. You can't see that up there. Come here, chlorine. Come over this way. All right, let's build a Bohr model for sodium. Actually, let's not even build a Bohr model. Let's build the Lewis dot structure for it. So sodium has one dot. Chlorine, look in the periodic table, has group 17, has a 7A up there, has 1, 2, 3, 4, 5, 6, 7 dots. Now last week we talked about the octet rule, where all elements want to have a full outside ring. Well, if you look here, at the moment, this right here has no charge. This sodium, it's a neutral charged atom. All right, there's no positive or negative charge. This chlorine, it's not positive or negative. They're not charged. They're neutral. They're happy. They're the ones we've been playing with all year until this unit. Now, sodium, though, does not have a full outside ring. Chlorine does not have a full outside ring. And let me actually, this might help if I draw the Bohr model here. I think that might actually help out. I know a lot of us are visual people. Give me a second, let me draw the Bohr model. Okay, let me get a smaller little ring. 1, 2. I always do that. Okay, there's 1. You want to just copy that one over to make things easy. Okay, so we got another one over here. All right, let's build the Bohr model. I'm just going to do the electrons. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Uh-oh, I needed one more ring around here. Let me erase that little gray again. Don't know why it does that. Well, it's a setting actually, it's probably why, but whatever. And 11. That's the Bohr model for sodium. Let me go to chlorine on the other side. All right, so chlorine's number 17 on the periodic table. 1, 2, first ring's full. Let's move to the next. 3, 4, 5, 6, 7, 8, 9, 10. Uh-oh, that ring's full, so I need to add another one. So it's gonna be a really weird ring, but it's okay. We'll resize that. But right there. All right, so we have 1, 2, 3, 4, 5, 6, 7, 8. Let's add 7 more. 1, 2, 3, 4, 5, 6, 7. All right, so the octet rule says all elements want to have a full outside ring of 8, except for the first row, they only want 2. But octet means 8. So sodium, it does not have a full outside. Chlorine, does not have a full outside. So what things can happen is, in ionic bonds, someone can give another one away. So sodium over here, like, I really want 8. So what I'm going to do, chlorine, how you doing? I'm going to be friendly over here and say, hey, I'm going to take this electron and I'm going to give it to you. So chlorine, you now have a full outside 8 on your ring. So does it have a full outside? 1, 2, 3, 4, 5, 6, 7, 8. Now chlorine is happy. Let's get sodium. Sodium now has this empty ring. Well, that's okay. It just disappears. Now does sodium have a full outside ring? 1, 2, 3, 4, 5, 6, 7, 8. It does. All right. So in the process here, let me just try to draw this in color. Sodium gave one of his electrons to chlorine. That's what happened. He's like, let's be friendly. Let's give it some water. All right. Black cherry water. All right. So sodium gave an electron to chlorine. But notice we haven't talked about the word bonding yet. Are they bonded at the moment? No, they just gave it over. Now, let's look at the charge. Sodium's charge, let me actually draw a little electron over here so we know that's what happened. So we don't forget about it. All right. Sodium's charge, well, let's see, it has, how many protons does sodium have? I can't remember. Let's look. As number 11 in the periodic table, so 11 protons. So P plus is 11. It now has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. So it now has a +1 charge. So sodium has a +1 charge. Let's look at chlorine. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Did I do that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Right? It has 18 charge. Well, not 18 charge, 18 electrons. So the energy cloud has -18. Chlorine has 17 protons. I look on the periodic table. So we have +17, -18. The overall charge is -1. So both of these are ions. Sodium, since it gave one away, has a positive charge. Chlorine, since it took an extra electron, has a negative charge. So now they're both ions. Now, I remember back when I was a kid, a little kid in elementary, I always played magnets. You ever see magnets where you got the little positive end of a magnet and you have a negative end of a magnet? What happens if you get them next to each other? They go and snap. They hold together. We call this electronegativity. It's where the electrical forces, that positive and negative, they slap together. Do I have a magnet up here that's going to help? I don't. But the magnets basically hold together because of positive and negative force. No, I don't have any magnets. Darn it. Alright, so that's pretty much how the whole thing works. Is one takes an electron and gives it to another. Alright, but it does when we have a metal and a non-metal. Alright. Let me do one more example here. Because, I mean, this is a pretty easy case. And we're going to go a little bit farther in the week and talk about oxidation numbers and writing out the formulas for these. Is this a little bit of small spice? Not much. Alright, let me pull a periodic table and just pick some elements at random here. And then play with it. Right, we need a metal and a non-metal. Let's see. Let's do potassium. K up here, potassium. Let's actually draw it in the nucleotide symbol setup. So we have 85, and it has a neutral charge at the moment. Let's pick a non-metal. No, ooh, that's messy. A non-metal. Right, let's do fluorine. Fluorine is non-metal. 9, mass being 19. All right, periodic table. Let's make you disappear. All right, so these are the two elements we're going to play with. Now we have a metal and a non-metal. Let's make these form an ionic bond, where the charges are going to hold them together. I'm going to draw, oh gosh, I'm using red there. Let's draw, let's do the Bohr model again. I think that might help people out. Let me draw a little, let me actually go back over here. Oh no, I didn't do that, I erased them. I'm going to try to copy it over. Maybe I saved it. Oh, there is one saved. Awesome. All right. Let me add another ring to it. Oh, that was too big of a line. Do 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 do. Maybe about right here. Let's resize it. It's still kind of big. There we go. Let's make two of these. Copy. Paste. All right. Potassium. Which element? Which ring is that? Okay, that's four. It needs 4 rings. Oh my gosh. Is that another ring for potassium? All right. And doop. All right, that should work. All right, so we're going to do it the same as we did prior. We have 19 electrons on this Bohr model. We start off with the protons, though. Protons plus is 19. Now, let's go ahead and fill in the neutrons, too. Why not? I mean, we just did that the other day. All right, with the isotopes. We do the same thing. So what's 85 minus 19? Well, 9 minus 5. Nope. So take 7 out of 15. There's 6. All right. Oh my gosh. I lost. Okay. So I have 9 out there. So we do 7, 15. We have 6 and 6. We have 66 neutrons. All right. Now let's add the electrons. We have a total of 19. So you have 1, 2. The first ring can only have 2. So we go to the next ring now. 3, 4, 5, 6, 7, 8, 9, 10. That ring now has 8. It goes to the next ring. This is full. 11, 12, 13, 14, 15, 16, 17, 18. Oh, that's now full. Let's go to the next ring. 19. We're now out of electrons. Easy peasy. Let's go to the next one right here. Fluorine. Let's put the protons and neutrons in the middle. That's 9 protons. This thing of fluorine has, see, 10 neutrons. Okay. Let's add the electrons to it now. We have a total of 9. First ring is 1, 2. Those are really big. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. We didn't even need that last ring. Look at that. So it's gone. All right. So we have these 2 elements right here. See, both right now are neutral charge. There is no other charge up there. They're neutral. Now sodium, he's still sad. Fluorine is sad. How can we make them stable where you have a full outside ring? Where it's sodium's, not sodium, potassium. Right now, if we drop potassium water, he's going to be really reactive. How do we make it where he's not going to be reactive as much? Well, he can say, you know, fluorine, you're kind of a cool guy. I'm going to give you my electron. And I'm going to do that because I want a full outside ring. I want to be happy. So we're going to take this little bitty electron right here. Oop. We're going to move him over here. All right. Can we do that? We absolutely can. Let me get rid of this. There we go. We absolutely can. We took that electron and we change that to like purple, and we gave it away. All right. Now let's look at sodium. What is our charge? Well, we have plus 19 in the middle, so we have a positive 19. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Minus 18 in the electron cloud. Overall charge is plus 1, or 1 plus. All right, let's go to the right-hand side. We have a nonmetal fluorine. It's a gas. It's actually the most reactive gases. It's in group 17. It's not the most reactive, but one of them. We have 9 protons. We have plus 9. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. So 9 is 10 charge. Our total charge is 1 negative. 1 negative. Well, since we have a positive negative charge, like magnets, these guys are going to go, hey, like this. They're going to stick together because it's ionic bonds. It's like positive and negative on a magnet. They're going to be bonded together because the magnets, or not because the magnet, the electromagnetic force. We have a positive and a negative. They're going to be stuck. This one, hi, we're stuck. We're going to go a little bit farther than that. There's a bit more, few more small details, but that's going to be when we hit oxidation numbers, we're really tied together. All right, well, that's this little tutorial video. I hope you have a fantastic day, and let's see about playing another little intro video going on.